Welcome everybody to the first seminar in December. So this time we have Gerardo Barrera Vargas. He's the new professor here at IFT in Lisbon. And well, Gerardo will talk about the asymptotic distribution of the condition number for random circular matrices. So Gerardo, the floor is yours.
Okay, thank you for the opportunity. Can you hear me?
Yep.
I hope yes. Okay. So today I will talk about this work about condition number for random circular matrices. I will provide all the details during the talk. You have some questions, please just unmute yourself and ask the question, please. Okay. Doesn't move. Okay. The menu for today is the following. I will start with some introduction, very briefly, talk about singular values, definition of condition number, some reference. Then I will jump to study the random circular matrices, provide the main theorem, the corollaries, consequence, etc. Then I will jump to provide something we call the analytical approach. I will explain with more details. I will explain how you can remove one singular value, then how you reduce to the bounded case, then you pass to the smoothness, and then you apply the so-called Komlós Major Tusnády coupling to get the result. And finally, I will provide some reference. Okay. So, given a matrix, no? Everybody knows what is an eigenvalue. No? An eigenvalue, as we know, is a number, a complex number, for which there is a non-zero vector, such that this relation AB equal to lambda B holds true. Okay. And then the next question is, what is a singular value? And this is a less common definition. No? And the definition is the following. So the singular values are exactly the square roots of the eigenvalues of the following matrix A star, where A star denotes the conjugate transpose of the matrix A. You can note from this definition that you don't need to request that the matrix is a square. It can be n times m, and this definition is still working. I will recall just some basic properties. No? This is always a square matrix. No? This is always symmetric. This is always non-negative, definite. And then the eigenvalues of A star are always a non-negative numbers. A star and A star A has the same eigenvalue. You can compute whatever you want. No? And also there is some invariance. No? The singular values of A and U1, A, U2 are the same when U1 and U2 are unitary matrices. Okay. And then let me assume now that the matrix A is a square, 3 by 3, 4 by 4, whatever you can imagine. And then the following question: are the singular values of A just the square root of the modulus of the eigenvalues of A? And the answer is no. And then let me give one basic example. No? We have this matrix, which is 3 by 3. You can compute the eigenvalues. It's 1, 1, 0, easily. However, the singular values are square of 3, 1, and 0. So the singular values, even for square matrices, is not just to compute the square root of the modulus of the eigenvalues of the square of the eigenvalues. It's not like that, okay? When the matrix is normal, then yes, the singular values are the absolute values of the eigenvalues of the matrix. No? But in general, it's false. Okay? If you want to know more about the singular value decomposition, I refer the following reference, but there are many. No? It's the classical book of Hoare and Johnson, etc. Okay, now I will talk about the so-called condition number. This is an old concept introduced in the 47, 51, 58, more or less, in these papers by Newman, Goldstein in numerical analysis, and Turing in they want to measure the following: how much the output of a linear system change when we have a small perturbation in the input. It's roughly speaking the definition. I will provide later more precise definition. And since then, it has been, let me give the definition before, okay? So I will define the extremal singular values. They appear in many, many areas of mathematics, like geometric functional analysis, mathematical physics, numerical analysis, time series, etc. Just recall, if we use the 2 norm, the minimum singular value can be computed by this expression, and the largest singular value can be computed by this expression. And when the matrix is square and invertible, the minimum singular value satisfies the following relation. And then the condition number is defined as follows: is the fraction between the maximum singular value divided by the minimum singular value, or in other words, this expression which is here. Okay? So, just to recall, the condition number is just the fraction between the maximum singular value divided by the minimum singular value. They are positive numbers, so it's a positive quantity and it's always bigger or equal than 1. Okay. Okay, let me give some idea of this definition. Let me assume we want to solve this system, AX equal to B. And let me assume that the matrix is this one, 1, 1, 1, 1.001, and B is equal to 2, 2. If we solve the system AX equal to B, we get that the solution is X1 equal to 2 and X2 equal to 0. Okay. However, if we perturb a little bit the output, like 2 in the first component and 2.001 in the second component, we get that the solution of the system is X1 equal to X2 equal to 1. So we can notice that a small perturbation in the output give a big change in the input. Okay. So in some sense, we can say that this system is not stable. In some sense. Let me be more precise later. So recall that AX is equal to B and the matrix A is invertible. So this notation is just a perturbation of the vector B. And then if I have a perturbation of the vector B, then I can find some vector delta X, it's just a notation, such that this happens because the matrix is invertible. In other words, this relation holds true. Then it's possible to show that the relative error, which is the error I do here, divided by X, this is the norm, is bounded by this quantity, which is the norm of the matrix, times the norm of the inverse of the matrix, multiplied by this. And this quantity, which is here, this norm of A times the norm of A inverse, correspond to the condition number. It's exactly the same definition, depends on the norm. I put the 2 norm in the previous slide, but this could be a definition of the condition number also. Also, we can see the following, that the relative error, this delta X divided by the norm of X, and delta B divided by the norm of B, because delta X, I can take the inverse, is exactly this. X is exactly this because of this relation, and I divide by this. I just put in a rearrange in a suitable way, and take the maximum over all perturbations which are not 0, and we get this quantity. So the condition number measure the relative error I do when I get some small change in my output, how this translates to the input. Okay, morally speaking. Okay. They appear, as I said before, in many areas. Has been studied by many authors, as you can notice in this slide. They are also studying in sample correlation matrices, and they are using also for studying Poisson statistics, and larger singular values or eigenvalues appears in many areas of mathematical physics, for instance. Okay. And I will now recap some literature about this topic. The limiting law of the condition number for random rectangular matrix with ID standard Gaussian entries can be computed explicitly. And then the exact law of the condition number of 2 by n matrix can be derived. This is done by Elderman in 88, this paper. And for real square random matrices with ID standard Gaussian entries, it's possible to get asymptotic lower and upper bounds for the third probability of the condition number. It's done by those authors in 2004. It's possible to generalize the previous expression for no square matrices and the analytic expression for the tail distribution. That was done by Edelman and Sutton in 2005. Also, lower and upper bound for the condition number in other norms, like the p-norms, and the so-called average loss of precision can be also obtained by, for real and complex square random matrices with ID standard Gaussian entries in the 91 by this author. Also, it's possible to study lower triangular matrices and analyze how with ID standard Gaussian entries and analyze how the condition number grows up. And it showed that this number converges almost surely to 2. It was done in 98. Also, there are some derivation from physics, something that people call column-free technique, and it's possible to derive the distribution of the condition number. It was very recently, 2004. And also it's possible to study large deviation, not only for ID Gaussian, but also for sub-Gaussian distributions. It was studied in 2009 by Anderson and Wells, and 2021 by Single, Umarija, and Wang. Okay, this is just some reference. There are many others. And you can notice that in many of the reference before, people are just focusing the ID Gaussian case, standard Gaussian entries, because it's the case in which we can do computation morally. Okay, so let me recall briefly what is a random circular matrix. A circular matrix is a matrix with the following structure. I give to you the first row, like nu0, nu1, nu2, up to nu n-1. And then I rotate this. And then I wrote this line. And then I rotate here. And I wrote this line and keep going. So you can notice that the diagonals are constant. And in order to define the circular matrix, I just need to define the first row, for instance. I say it's random when this nu0, nu1, nu2 up to nu n-1 are random variables. Okay. Due to this circular structure, it's possible to diagonalize these kinds of matrices. One can define the so-called Fourier unitary matrix. It's just to take the n primitive root of the unity, defined by omega m. I define the powers of this matrix. I rescale by square of n to normalize. And then any circular matrix can be diagonalized using the Fourier matrix. This basis induced by this Fourier matrix work for all circular matrices. Because typically what we have, for instance, if we have a symmetric matrix, we know that there is a basis in which you can diagonalize. But here not, any circular matrix can be diagonalized using the Fourier matrix. And in the matrix, Dn is the diagonal, and the eigenvalues can be computed explicitly by this formula. Just using the entries and the powers of the primitive n root of the unity. Okay? So as I said before, when the elements are random, we say that the matrix is a random circular matrix. And using the previous formula, this is the formula for the eigenvalues. And also, one can show, one can see easily that the circular matrix is a normal matrix. Then the singular values are just the modulus of the eigenvalues, as I mentioned it before. And then the string singular values of the random matrix is given by this. This is the minimum of the absolute value of the eigenvalues, and this is the maximum. Okay, we have an explicit formula here. Okay, and then the condition number is a random condition number now. It's just the fraction between the maximum singular value divided by the minimum, whenever the minimum is positive, whenever the matrix is invertible. No? So you can observe that the maximum and minimum are not independent, they are correlated. Then it is not easy a priori to compute or estimate the distribution of the condition number. Okay, let me assume the following condition. I will assume that my random variables are not degenerate. You can assume they have mean 0, variance 1, for instance, but also I will assume that they have a little bit more than the second moment, the moment 2 plus delta, something which is called the Lyapunov condition in the literature. Okay. And for instance, sub-Gaussian random variable not degenerate satisfies this condition. It's a very weak condition. Okay, and the main result is the following. If I compute the joint distribution between the minimum singular value and I normalize the maximum singular value suitable, they decouple in the limit. So they are asymptotically independent. This R is the Rayleigh distribution, and this G is the Gumbel distribution, and the constant here, an, is given explicitly here. It's a square of n log of n over 2, and the constant bn is given explicitly here. So the results say that if I want to compute the joint distribution between the minimum and the normalized maximum, it goes asymptotically to a product of Rayleigh and Gumbel distribution. Okay. We can see easily that the normalized maximum are asymptotically independent. It goes to the Gumbel distribution. The minimum goes to the Rayleigh just by projection. But something which is less clear, what happened with the fraction between the maximum and the minimum? Because since they are correlated, it's not easy to deduce exactly which is the correct limit. So we can show that the condition number goes to a Fréchet distribution when you normalize by this quantity, and this Fréchet distribution has the following shape exactly. This is the law. Okay, I will give some remarks. When the Gumbel law appears as a limiting law of extremal singular value, this is common. I will say the Gumbel law appears as the maximum of many stuff, the maximum of the peridograms. For instance, in 2009, Brick and Seturaman showed that the Gumbel distribution is the limiting distribution of a renormalized large singular value for symmetric circulant random matrices with ID sequence, just half of them, no? Because it's symmetric, satisfying the Lyapunov condition. Okay. Also, it's possible to show that after normalization, the limiting law of the largest singular value or Hermitian Gaussian circular matrix is Gumbel. This was shown by Mekis in 2009. And also some limiting, this is not limiting, this is like large numbers have been shown for random matrices with ID Gaussian matrix. Okay. When the Rayleigh distribution appears as a limiting of a small singular value, this is less clear, no? To be honest, this is the only reference I know, no? So when the matrix has ID complex Gaussian entries, we can compute explicitly the distribution of this guy n times the minimum singular value, and this is a chi-square distribution with 2 degrees of freedom. This is not asymptotic. This is for all n. It was shown by Edelman in '88. And in the real case, a little bit more complicated, but it's possible to do also. And you can also characterize the limiting law. There is an explicit density. It's also done by Edelman in '88. It is less clear where the Rayleigh distribution appears. The unit reference, more or less, I know is the following. So you can notice that the square root of an exponential distribution with parameter lambda correspond to the Rayleigh distribution with parameter 2 lambda to the power -1/2. And the exponential law appears as a limiting distribution of the minimum modulo of trigonometric polynomials. It was shown by Yakir and Zeitouni in 21 for the Gaussian case, and Cook and Guillem in 21 also for the Sud-Gaussian case. Trigonometric polynomials are the formulas we have for the eigenvalues are very similar, no? Because I am taking the square root of the unity, so they are correlated, this kind of result. Okay. When the Fréchet distribution appears as a limiting distribution of condition number, no? So if I study the matrix AN, which is a random matrix with ID complex entry, yeah? The condition number of this matrix divided by n goes to a Fréchet distribution. It was computed explicitly by Edelman in 88. When the entries are real, no? They were complex, no? It goes to a random variable, no? With explicit law, also explicit density, and also it was computed by 88. However, this law doesn't belong to the Fréchet family of distribution. So for the complex case, it goes to a Fréchet with some parameters, but for the real case, it doesn't go to a Fréchet. Okay. So having this in mind, let's show now the item 4, no? That the condition number goes to a Fréchet. Okay, the condition number is the difference is the fraction between the maximum and the minimum, but this is just an equality, no? Just sum this quantity and sum and erase. No? Using the definition of Bm and Am, we can see that Bm divided by this quantity tends to 0, no? And Am divided by this quantity goes to square root of 2. So by the Slowski theorem, since this quantity tends to 0, we can see that this tends to 0. And this quantity, this tends to square root of 2, and 1 over the minimum goes to 1 over the Rayleigh. No? So we have this limit. No? So even though this part and this part are correlated, no? Because the maximum and the minimum are correlated, since the first limit tends to 0, I can use again the Slowski theorem and deduce that the condition number goes to square root of 2 divided by a Rayleigh distribution in law. No? And then a computation showed that square root of 2 divided by Rayleigh correspond to a Fréchet distribution. Okay? The same can be done for the powers. For the powers, we can compute the powers as a circular matrix. We can shift the mean, divide by the correct quantity, and it goes to a Gumbel. The minimum goes to a Rayleigh, but we need to rescale a little bit here. And the condition number the same. We need to properly normalize, and it goes to a Fréchet, and we need to rescale here. Okay? This is just some change variable. Okay, well, and what is the method to prove this kind of theorems and results? No? As you can see in the reference I provided before, in many of the papers, people focus just in the Gaussian case, no? Because in the Gaussian case, there is some hope to do explicit computation. No? And here the idea will be more or less the same. No? We will compare the distribution of the smallest singular value or the largest or the joint law with the distribution of the smallest singular value of a Gaussian random matrix. So now my matrix will be Gaussian, a suitable Gaussian matrix I will define later. So for the Gaussian case, I can get some formulas, then I can compute the correlations, and then I can compute exactly everything as I want. No? And then from the Gaussian approximation, we can go to the general case by the so-called Komlós Major Tusnády coupling that I will present below. So the idea is the following. This is my original problem. I will compare with some minimum and maximum of some Gaussian approximation. and I will show that the difference is small. And I will not give all the details because there are many, but I will give the main steps in the proof. Okay. So the first observation is the following simple relation, that this joint law can be written using just set like this, and I don't need to assume any independence. It's just a computation, and we can show that that this is less equal than this minus this set. Okay, so in the following, we will compute just the probability of these events. Okay, and we start showing that it's possible to remove the first element, the first singular value. The first singular value, if you recall here, the formula, which is difficult to recall, it's a random walk because k is equal to 0, and it behaves different from the others. And using the central limit theorem, we can remove the first singular value from the computation because it behaves different from the others. Okay. And then, since we only assume the 2 plus delta condition, the Lyapunov condition, now we will use some truncation procedure, very standard. We take this truncation in this power and erase the mean to be mean 0. And using Borel and Telly, one can show that if we define now my new, let's say, my new eigenvalues by this, using these random variables, one can show that the difference between them, the biggest difference between them is 0 with probability 1, asymptotically. So we can replace everything using these variables. This is an application of Borel and Telly. Okay. And then we define now our condition number with tildes when the random variables are bounded. This is the minimum, this is the maximum. And then one can show, using the previous lemma, that the problem I am interested is asymptotically equivalent to the problem in which I assume the random variables are bounded, as in the lemma. Okay? But how the Gaussian perturbation works? The idea is to use a modifier. So I will take an array of random variables with a standard Gaussian distribution. I will take a small deterministic sequence of positive numbers. In a way, the following limits holds true. This is deterministic. So I can anticipate that this quantity is more or less n to the power minus theta for some specific exponent theta that I will define later. And having these variables, I can define the following. I take slide my singular, this is the equation of the singular eigenvalues, and then I multiply by this small quantity. This quantity corresponds to the eigenvalues of a circular matrix with ID entries, and the entries are Gaussian, given by this n1, n2, up to n minus 1. Okay? This is just a perturbation by a circular Gaussian matrices. And then, using this special beta, I define the minimum to be beta m, and I take this perturbation to the bounded case, and this is the same perturbation. This is the minimum, the maximum, and I define this quantity. And the main theorem is the following. If I show that the bounded case goes to the product of Rayleigh times Gumbel, I finish. Why? Because of this. Because I reduced already the problem to the bounded case. So this is the main theorem now. If I show this, I finish. But to show this theorem, it's possible to show that it is enough to show the same for the perturbation using the Gaussian. Now, if I use the perturbation using the Gaussian, I have my variables are bounded, they have a smooth density, and then I can use a quantitative coupling. So everything can be reduced to prove the following lemma, that the minimum can be less equal than beta n x. Let me recall what is beta n. Beta n is exactly this quantity. And the maximum is less equal than beta n this quantity goes to this product. Okay. And then I do many reductions. I start with my Lyapunov condition, then I erase the first singular value. Then I reduce to the bounded case, and then from the bounded case, I apply some modifier using Gaussian, and then I reduce to prove this lemma. Okay. Okay, let me recall the Komlós Major Tusnády coupling. So let me suppose I have a distribution with exponential moments. This is the Laplace transform. Let me suppose for simplicity that the mean is 0 and the variance is 1. Then the Komlós Major Tusnády coupling says the following, that there is a probability space such that we can construct two sequences of random variables. The random variable x they are ID with common distribution capital F, and the random variables in the sequence y, they are ID with a standard Gaussian distribution. And moreover, for any x and for any m, we can estimate the difference between the random walk, the original one, let me call with this capital X, and now they are approximated by the Gaussian. And the error we do is at most log m. So in other words, what is say, when you have a random walk, you can always replace by a Gaussian random walk, and the error you are doing by the replacement is something which is about log m. And it's something quantitative that we can estimate the probability. Okay, that will be the idea of the theorem. Yeah? But here we need something a little bit more sophisticated, no? Because in the formula for the eigenvalues are not just a simple random walk. No? They have some random walk, but we have the square root of the unity. They are rotating. No? And since they are rotating, we need a new version of this Komlós Major Tusnády, which is called the Einmahl Komlós Major Tusnády approximation. No? Let me define this vector of frequencies that people call like this. No? And using this vector, one can show that this quantity, this is the truncated, then I perturb by the Gaussian, which are independent, exactly as I defined before. I multiply by the vector of frequencies, and this is very specific. This is the constant that I need to choose. And then I have the approximation of the density of this guy is exactly the density of the Gaussian. No? This is the density of the Gaussian. This is the covariance matrix, and can be done up to this regime. Yeah? And everything is more or less explicit. It's not super explicit, but so but this is very quantitative. No? So this is exactly the quantity that I have now. No? For a reason, I choose to do the modifier in that way, in a way that, and this is related with the b time. No? And now I can apply this theorem. No? That I can replace this for a suitable Gaussian, no? And for the Gaussian, I can do the computation. That's the idea. Okay, so what is the brief idea of the proof? Is the following. I want to estimate this quantity and this quantity. And just by definition, this is exactly this minus this. But the eigenvalues came in complex conjugate, then I can use just the half. No? And then using just the half, I get this, no? Because I don't want to count dependence there. And then I just define this probability by this. And then we will show that in the limit, this probability goes to this exponential. And that should be enough to conclude the theorem. I will explain why. So in order to analyze this probability, I will analyze the complement of this event. So this is the event. I define with the complement. I define 1 minus this probability is 1 minus this, and this is just the union. No? And then I use the Bonferroni inequality, but using the lower bound and the upper bound, both I need. No? And this is exactly the relation. No? And this Jn is given by this. However, we can compute exactly these events, that is Sjm, no? And we can show that these guys goes exactly to this. And then you can substitute D to be J if you want. And then you replace this guy here, no? In the upper bound, and in the lower bound, you send L to infinity, and you get exactly the product of the Gumbel and Rayleigh, exactly, no? The probability of that. Okay, and then the proof is complete. So the proof is given in several steps, no? This is more or less the method, but the idea is replace everything by a Gaussian approximation and then formalize everything doing this Einmahl Komlós Major Tusnády approximation. Okay. So let me give a summary of the results. What we prove? We prove that the joint distribution between the minimum and the normalized maximum, they are correlated, they are not independent, but in the limit, they decouple and they become a product between the Rayleigh and Gumbel, no? And the constant A, N, and Bn are completely explicit. No? I am just talking for the circulant matrices, satisfying the Lyapunov condition with zero mean and variance 1. No? And also I recall that then the projection goes to the Gumbel of the maximum, the minimum go to the Rayleigh, and the condition number go to the Fréchet. No? And what is next? Right? What we are trying to do now? Right? We are trying to extend this result for the case of top-list matrix. No? What is top-list matrix? In order to define a top-list matrix, you need to define two n numbers, nu 0, nu 1, up to nu n minus 1, nu minus 1, up to nu minus n minus 1. I need to give the first column and the first row, and then you can notice that all the diagonals are constant. No? And they appear in many applications. These top-list matrices are very important. And we are trying to understand the condition number for these kinds of matrices. The first difficulty we have is that in the circulant case, what was the magic? The magic is that we can diagonalize using the Fourier transform, and then we have explicit formula for the eigenvalues. Even the eigenvalues are a little bit complicated. They are not so complicated because they are more or less simple random walk. They are rotating, a little bit mess, but they are simple random walk. And then we use this Gaussian approximation, and we can get everything. The first difficult step here, that even in the we don't have access to the formula of the eigenvalues, no? or even worse, the singular values, because not all top-list matrices are normal. No? So knowing the eigenvalues is not enough, no? But let me suppose they are symmetric and then they are normal. But even in that case, we don't have access at a beautiful formula as we have for the circular matrices. No? So this is the first step we cannot do. Okay? We did some simulations. This is for the minimum. Okay? And we can note that the minimum appears to converge to something. This something is we can check, is a Weibull law. We need to fix the parameters, but the minimum belongs to the Weibull family. And just to note that the Rayleigh distribution also belongs to the Weibull family. We believe that also the maximum should belong to the Gumbel after normalization. And maybe we should be able to do the condition number for the top list, but up to the moment, we are not able to do that. Okay? And the reference, this is the paper I was talking today. This is the paper by Baker and Seturaman. This is a good book to, this paper, to start to study probabilistic analysis condition number. The method I talked today is given in this Davis and Mikosh, no? When they analyze the maximum of the periodogram. No? This is the paper of Edelman that I mentioned several times, and this is the paper in which there is this quantitative extension of the Komlós Major Tusnády coupling. Thank you.
Thank you, Gerardo. So you were quite fast. So we have questions from the audience, from Zoom. I know them. Oh, no. No. I think there is one. This one. You better we don't hear. Or maybe it's me.
I guess I could ask
Hear me?
you.
No, no.
Oh,
Yeah,
I'm
we
sorry.
hear you. Oh,
Please go ahead,
Okay.
Sundar. I was
Yeah,
testing the
yeah.
microphone.
Oh, okay. No, sorry. Nice talk, Gerardo. I was just wondering, are there other types of matrices? Hankel also, are you considering?
We try, but we cannot also do the Hankel easily. It's not easy. So as you can notice, everything now is based on this Komlós Major Tusnády, and we need this. We basically we start from here, and if we have an expression something like this, we can repeat the steps. But even for the Hankel, we cannot do something like that. We try to do bounded tuplets. They are very difficult also.
I see.
By simulation, it appears holds true, but that is not enough.
I see. So do you expect to get the same sort of answer as in
Yes.
circulant?
Yes, we expect that it belongs to the Fréchet family. Not exactly the same Fréchet, but it's because even for the tuplets that we have here, we did simulation for I didn't put all the simulations, but we did simulation for Gaussian, we did simulation for Rademacher, and all goes to the same limit when you don't need to normalize. This is the minimum. And then we check the parameters, and then it belongs to the Weibull distribution, morally. So we expect some universality.
Okay, well, thank you very much.
Okay.
Are there more questions?
Yes, I have a question. Yes, so when you consider your circulant matrices, are the coefficient real, the xi?
Sorry, can you repeat?
Your random elements, are they real random variables?
In this setting they are real, but something that happened in this kind of setting, that the complex case is many times easier than the real case. But the theorem,
it doesn't seem to change a lot. Well, in particular, if you take complex Gaussians, you have the advantage maybe that all the random, all the eigenvalues have the same distribution, for instance. But
yes. But this theorem is stated for the real case.
okay.
But
And,
it doesn't change too much if you go to the complex case. It's possible to do also.
And the result you get, okay, I mean, okay, the random variables you have, okay, they kind of look like, your eigenvalues, they kind of look like Gaussian, right?
Yeah. Yes.
And I guess if you take them pairwise, they are almost independent. Is the
Yes.
scaling you obtain the same as that you would obtain for IID Gaussians or independent Gaussians with the same parameters, or do you get some?
You are talking.
Is there some macroscopic effect of the dependence here?
Okay, you are talking if I take Gaussian with let's say
if you
zero.
replace your lambda kn by IID Gaussians with the same mean and variance, would you get the same convergence for the minimum modulus and the maximum modulus, or would you get something slightly different?
It's a good question.
I think the law would be the same, but I'm not sure about AN and BN and the scaling.
Yes. I need to point out that if we try to do this, what is the idea of the proof? The proof is easy. If you replace this by Gaussian, yeah, we can compute the modulus square. This becomes some chi-square. And then we compute the correlations, and we can notice that they are independent because that's enough for Gaussianity. And then we can compute the maximum and the
okay,
minimum.
so they are in the so in the Gaussian case they are independent.
Yes, in the Gaussian case
okay,
they
okay,
are
okay.
exactly
So I
independent.
thought you had some weak dependence. Okay, so they are exactly independent.
Yeah.
Okay.
They are exactly independent because I am assuming that all here all the entries psi 0 to psi n-1 they are independent. Yes.
Yeah.
So it's a torus force. You can show exactly the result in the Gaussian case.
Yeah. I guess it might just be a trivial consequence of the fact that your column in the Fourier matrix they are orthogonal, so this gives you zero code variance.
Yes, exactly.
Sure.
Yeah, indeed, the complex Gaussian case is easier than the real case, but yes.
Okay. Thank you.
Okay.
Right. Are there more questions? No? All right, so let's thank the speaker. Thank you, Gerardo, for this very, very nice talk. Beautiful.
Okay.
And I think let's continue next week with you, Clement, right? You are the host for next week, I believe. Maybe not. I don't know.
I don't think so.
Okay, who is doing it next week? Do you know? Anyway, okay. Take care, go to the website and it will be announced soon.
To replace Pietro?
But that's the week after, no?
Yes.
So no, actually not. And I just learned that the majority of people at IMPA will be in Korea.
Okay.
Yeah, on the 18th. I'm talking about the 18th.
So maybe it's better to just cancel the 18th, no?
Yeah, maybe let's cancel the 18th. And next week it's already announced, and we just don't know who's hosting, but it's fixed. But maybe we
Tommaso,
go
right?
on break.
I think it's Tommaso.
Yeah, I think it's is it Tommaso speaking?
Tommaso.
Yeah, I think so.
So I think we'll host him, I guess.
Okay.
Great.
All right.
So then we
Perfect.
enter a break after the 11th.
Fair enough. Yeah, so I offered Pietro the next available slot for me, which was in way later in May.
Okay, perfect. So see you next week on Wednesday. Thank
See you.
you.
Bye-bye.
Bye-bye.
See you.